Hello again, and welcome to part 2. In this part, we'll be covering the characteristic equation, which you've all been waiting for. We'll discuss how to find the distinct roots of homogeneous systems, and we'll address the special cases, namely imaginary and repeated roots. If you recall from part 1, we covered vector addition. We also covered the linear independence of vectors and later functions. And we also showed how to obtain solution sets with a combination of vector solutions. If you haven't seen part 1 yet, Dayton informs me that the subscribe button below is a very good link to that video. Otherwise, there's one in the description. So, finally, here it is, the aptly named method of undetermined coefficients, which uses a system's distinct roots to derive the form your solution will take, and with some additional information, typically in the form of initial condition, allows you to actually solve. So, let's consider a differential of this form. ay double prime plus by prime plus cy, and we'll make this a homogeneous system. First, let's make an assumption. Let's just assume that solutions for y of x will take the form e to the rx, where x is the function's operating variable and r is some constant that we don't yet know. Now, I know this is just an assumption. We can't necessarily say that this is true. However, we can find cases in which it is true. So if y of x is e to the rx, that means then that y prime of x will be given as r e to the rx. And the second derivative, of course, will be r squared e to the rx. Let's go ahead and substitute these in to our differential equation, and we'll just write that out. So we have a r squared e to the rx plus b r e to the rx plus c e to the rx equals 0. And each of these terms share an exponential, so let's just go ahead and factor that out. So then we have e to the rx times the quantity ar squared plus br plus c equals 0. Now, there's something very special to note here. E to the rx is not equal to 0 for all r and for all x. This is an important realization to make because that means then in turn ar squared plus br plus c, if this is true, must then equal 0. Well, this is a quadratic equation. We know how to tackle this. This must then be true when r equals, well, negative b plus or minus the square root of b squared minus 4ac all over 2a. As you can see from this quadratic expression here, we're going to have two values of r, due to the plus or minus sign right here, that actually allow this to be true, which means that that differential will have two solutions for y of x. So if you'll recall from before, we said that linearly independent functions, or functions that are not scalar multiples of each other, will constitute a basis. So if we have two, we can then say that the expression for y of x is given by c1, so some constant, times e to the r1x, where r is one of the two values that satisfies this, plus another constant, times e to the r2x. Another way to phrase this would be that the solution has a basis of e to the r1x, e to the r2x. So let's do a quick example and put what we now know onto paper. So if given the differential equation 2y double prime minus 7y prime plus 3y equals 0, and recalling from before, we're going to let y be e to the rx, and then its first derivative, of course, is r e to the rx, and the second derivative, r squared e to the rx. We can go ahead and substitute these into our original statement, so that would be 2r squared e to the rx minus 7r e to the rx plus 3 e to the rx equals 0. And as before, we'll go ahead and factor out the exponentials. So this is then e to the rx times the quantity 2r squared minus 7r plus 3 equals 0. And since we know that e to the rx cannot be 0 for any r or any value of x, we can simply write 2r squared minus 7r plus 3 equals 0. So in this case, for this quadratic form, we have then that a is 2, b is negative 7, and c is 3. So let's perform the quadratic equation and see what values of r satisfy this. R is then the opposite of b, so negative 7, so positive 7, plus or minus the square root of b squared, so 49, minus 4 times a, which is 2, times c, which is 3. And this is, of course, all over 2 times a, and a is 2. Simplifying, we have 7 plus or minus the square root of 49, minus 4 times 2 is 8, times 3 is 24, all over 4. And simplifying further, 7 plus or minus square root of 25, all over 4, or simply 7 plus or minus 5 over 4. And we now have two solutions. So first, let's address the positive case, so 7 plus 5, which gives us 12, divided by 4 is then 3. And for the negative case, 7 minus 5 is 2, divided by 4 is 1/2. So the two values of r that satisfy this are r1 is 3, and r2 is 1/2. Using the general equation that we had before for y of x, we then have y of x is c1 e to the r1x plus c2 e to the r2x, and we know r1 and r2, so let's put those in. Y of x then takes the form c1 e to the 3x plus c2 e to the 1/2 x. If you thought the case that we did in the previous example was rather convenient, you're correct. That's only what you do when you obtain real roots. However, as I'm sure you recall from the quadratic equation, it's very possible to obtain imaginary roots as well. And I'm sorry in advance for how heavy the math gets here. And also, I normally like to write things out for you. However, due to how many mistakes can be made in all of this writing, I went ahead and wrote it all out for you in advance. So, as we discussed earlier, a differential in descending powers of derivatives, as such, we re-express like this. So, whenever b squared minus 4ac is less than 0, we're going to get complex roots. And the complex roots are going to always take this form, in which we have a real component plus or minus the same imaginary component. So, our general solution then, substituting r1 and r2 into the form that we had previously, will yield something that looks a lot like this. If we factor out the real component by separating the exponential into the real and imaginary parts and then factoring, we can obtain something that looks like this. We can't stop here though, because we have imaginary terms inside the exponential. So, at this point, our buddy Euler has a nice expression for us that's going to change our form into trig functions. So, according to Euler, e to the iax can be rewritten as the cosine of ax plus an imaginary unit times the sine of ax. So, if we impose Euler's identity on what we have written here, we'll arrive at something that looks a lot like this. And I know this is very long, but essentially we've just taken this exponential term right here, and we've re-expressed it in terms of cosine and sine, and we've done the same to this term, except you can see how the negative has found its way inside the trig functions here. The problem here is that we have trig functions with positives inside them here, and negatives inside them here, so we cannot group these yet. Let's recall what we know about the unit circle, however. Positive and negative angles, so long as they're the same angle, the positives and negatives will have the same cosine component, right? So this is the cosine component right here. And as you can see, this positive angle and this negative angle share the same cosine component. We may then write that the cosine of ax is the same as the cosine of negative ax. That is, the cosine component of the positive and negative angles are the same. On the contrary, for sine, the positives and negatives of the same angle have opposite components. So here are the sine components. Here's the positive angle's positive sine component, and the negative angle's negative sine component. So then the sine of the negative angle is the opposite of the sine of the positive angle. So we may write this expression. If we make substitutions by these trig identities that we know to be true, we can re-express this function right here in terms of trig functions that share terms on the inside of the trig function that allows grouping. So if we do that, we can then group our trig functions such that the coefficients can be grouped. So, from the previous page, we had this written, where we had grouped the components in front of the sine and the cosine components. This is useful because we've gone from 4 terms down to 2. However, we still have an imaginary term in front of our sine function. So, the way that we address this is a little convoluted, but bear with me. Nothing mandates that C1 or C2 be real numbers. So, let's allow them to be complex numbers. And a linear combination of parts of these imaginary terms, these complex numbers now, can be written as such, where P and Q are an element of the real numbers. So, if there exists a P and a Q such that this may be true, we may then substitute these for C1 and C2 into the previous expression. Doing so, we're left with this expression right here. And as you can see, I have replaced C1 with P plus IQ and C2 with P minus IQ, and the same over here. You may notice that in this term, we have a positive and a negative term for the IQ. That allows them to cancel such that we only have the P terms in front of the cosine. This is good because we're left with only a real coefficient in front of our cosine term. Over here by the sine term, this is convenient because the P terms cancel, leaving us with only the IQ terms. This does leave us with an imaginary unit in this coefficient. However, we actually want that because that imaginary term will cancel with the imaginary term that's already in front of our sine term here, thus leaving us with simply a -1. So, if we reduce all of these, we are left with simply e to the alpha x, so we've still got this real component from before hanging around, and then we have our trig functions with, by George, only real numbers in front of them and within the trig functions. And since P and Q are an element of real numbers, we may then express a general form for y of x as e to the alpha x times the quantity of some unknown coefficient times the cosine of beta x plus a second unknown coefficient times the sine of beta x. So we will use this as our general form for approaching imaginary roots. So let's do an example in which you get some imaginary roots. So given the differential equation, y double prime minus 4y prime plus 5y equals 0, I'm sure you're all comfortable putting y equals e to the rx and its derivatives in, so we'll go ahead and jump up to the next part. So we then know that e to the rx times the quantity r squared minus 4r plus 5 must then be 0. So in this case, we have that a is 1, b is -4, and c is 5. So let's solve the quadratic equation and see what values for r allow the statement to be true. So we then have that r is the opposite of b, or 4, plus or minus the square root of b squared, so 16, minus 4 times a is 1, times c, which is 5, and all over 2 times a, which is 1, so we'll just leave that as a 2. And simplifying, we have 4 plus or minus the square root of 16 minus 4 times 5 is 20, all over 2. And further reducing, we have 4 plus or minus the square root of negative 4, all over 2, or 4 plus or minus 2I over 2. And we can kill this 2 in the denominator and just write this as 2 plus or minus I. In this case, our complex number has an alpha value, or a real value, of 2, and our complex part, the coefficient in front of the I, is 1. So if you recall the general statement that we used before, it was y of x equals e to the alpha x times the quantity c1 cosine of beta x plus c2 sine of beta x. And this is not that bad at all. We actually have alpha and beta right here. So let's go ahead and put those in. And we can then say that the particular solution, I'm sorry, not particular, but the form that y of x will take will then be e to the 2x times the quantity c1 cosine of, well, beta is just 1, so then the cosine of x, plus c2 times the sine of x. There you go. That wasn't so bad. Let's do a harder one. So let's consider the differential equation 6 times the fourth derivative of y plus 11 y double prime plus 4y equals 0. And since we have a fourth order derivative this time, we should expect 4 solutions. So again, I'm sure you guys are already comfortable putting in y equals e to the rx and its derivative, so I'll jump to the next part. So we can then say that e to the rx times the quantity 6r to the power of 4 plus 11r squared plus 4 equals 0. I actually recommend having a, not necessarily quadratic solver, I'm sure you guys are proficient at that, but quartic, quintic solvers, cubic solvers, those are useful to have in these contexts. So if you put this through a quartic solver, you will see that it factors to the quantity 2r squared plus 1 times the quantity 3r squared plus 4. And we then have 2 roots contained in this term and another 2 in this term. So let's first consider case 1 right here. So if this term is equal to 0, let's solve for the 2 values of r contained in this term. So we'll just call it r1. We're going to have a plus or minus, but we'll just call it r1. We'll then say that it's equal to the opposite of b, and we don't have a b, so that's 0, plus or minus the square root of b squared, which is again 0, minus 4 times a, which is 2, times c, which is 1. And this is all over 2a, so 2 times 2. Simplifying, we have plus or minus the square root of negative 4 times 2 is 8, all over 4, or plus or minus 2i square roots of 2 all over 4. So we've got a 4 inside of here, that's where we get the 2, and then that leaves us with another 2, so the square root of 2, and the negative 1 becomes the I. In this case, we can reduce the factor of 2 in the numerator with one of the factors of 2 in the denominator, and this then becomes plus or minus I root 2 over 2, and I have one factor of root 2 in the numerator, and this is 2 factors of the square root of 2. So I'll cancel this root 2 with one of the 2 root 2's down here, and this then becomes plus or minus I over the square root of 2. So in this case, alpha is 0, we have no real component, and beta is then 1 over the square root of 2. So, how about case 2, where 3r squared plus 4 is equal to 0? Well, in this case, we have, again, no b term. So 0, plus or minus the square root of 0, minus 4 times a, and in this case a is 3, times c, which is 4. And this is all over 2 times a, which is 3. And simplifying, we have plus or minus a square root of negative 4 times 4 is 16, times 3 is 48. And this is all over 6. 48 has a factor of 6 and 8 in it, so we can write this as plus or minus I square root of 6 square root of 8 over 6. And as before, we've got a square root of 6 here and 2 square roots of 6 in the denominator. So we can say that this is then plus or minus I square root of 8 becomes 2 square roots of 2, and we still have that square root of 6 in the bottom. Then plus or minus, well, the square root of 6 becomes square root of 2 square root of 3, and we still have the I times 2 root 2 in the numerator. And then canceling our root 2's, we are then left with plus or minus I times 2 over the root of 3. And in this case, we then have that alpha is, again, 0, and beta is then what the I component is multiplied, so 2 over root 3. So, as we mentioned earlier, we should have 4 solutions for this because we're dealing with a 4th order derivative here. So, recall that our particular solution for a 2nd order derivative was given by y of x equals e to the alpha x times the quantity c1 cosine beta x plus c2 sine beta x. And we're always dealing with linear combinations here. So in case 1, we can express like this, and then we'll simply tack on another e to the alpha x times the quantity, we'll call it c3 now, cosine beta x, plus c4 sine beta x, where these, the alpha and the 2 betas up here are from case 1, and the alpha and the 2 betas down here are from case 2. So our form for y of x, in this case, will be given by e to the alpha 1x, so that is 0x, times the quantity c1 cosine of beta in case 1 was 1 over the square root of 2, so we have x over root 2, plus c2 times the sine of x over root 2, and then addressing the second case, plus e to the alpha 2x, which is again 0, so 0x, times the quantity c3 cosine of beta 2, so that is 2 over root 3. So inside the cosine term we have 2x over root 3, plus c4 times the sine of 2x over root 3. And we can, of course, get rid of the exponentials out front here with the real terms because they are exponentials with a 0 in the exponent. So then y of x will take the form c1 cosine of x over root 2 plus c2 sine of x over root 2 plus c3 cosine of 2x over root 3 plus c4 sine of 2x over root 3. Okay, so one more example dealing with imaginary terms. Let's consider if we have the 4th derivative of y plus 4y equals to 0. And again, we're going to go ahead and arrange it in this form. And if you don't have a quartic solver, you can factor this using the difference of squares. I know it doesn't look like a difference, but here's what the difference of squares looks like. So you can actually re-express it like this with an imaginary term here to allow it to be a difference. And then if you go ahead and factor this using the difference of squares, you'll see that you get case 1 and case 2, right? Case 1 and 2, right there. So we now have two solutions within case 1 as well as two solutions within case 2. So let's first consider case 1. And this one I've opted to solve with the quadratic formula. We can say that then for case 1, r is given by, well, there is no b term, so this just becomes plus or minus the square root of -4 times a is 1, times c is 2i all over 2a. So reducing, we have plus or minus 2 square roots of 2 times the quantity I square roots of I over 2. And we can get rid of both of these 2's, and we can combine these i's inside the radical. So we then have plus or minus square root 2 square root cubic I. Now, at this point, you're probably wondering what in the blazes we do with the square root of cubic I, or the square root of I, or anything like that for this matter. There's a couple of Euler identities I want to point out first. Consider e to the pi I over 2. If we apply Euler's identity, this becomes then the cosine of pi over 2 plus I times the sine of pi over 2. And if we go and evaluate these, we see that this is simply 0 plus I times 1, or I. If we go another halfway around the unit circle, we can consider e to the 3 pi I over 2. So this then becomes the cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. And again, the cosine term will evaluate to 0 because we're dealing with a perfectly vertical line right here. And the sine term this time, however, is -1. So this will give us an expression for negative I, whereas the previous one gives us an expression for positive I. So, knowing this, we can then re-express this I term right here, the square root of cubic I, and we can write r as plus or minus the square root of 2 times I to the power of 3/2. Imposing the Euler identity for I, this then becomes plus or minus the square root of 2 times e to the pi I over 2 raised to the 3/2 power. And if we combine the exponents here, this then becomes plus or minus the square root of 2 e to the 3 pi I over 4. Now we can use Euler's identity on this exponential term and get this into trig functions. So let's do that. This is then plus or minus the square root of 2 times the cosine of 3 pi over 4 plus I times the sine of 3 pi over 4. And I went ahead and plotted that up here. So pi over 4 is this 45-degree angle right here. And we have 3 of them. So 2 of them would put us at the 90, 3 of them would put us right here. And the magnitude of the sine and cosine components will be equal, but the sine will be positive and the cosine negative in this case. And they each have a magnitude of the square root of 2 over 2, or simply 1 over the square root of 2. So we can then write this as plus or minus the square root of 2 times the quantity, the cosine component is -1, right, negative, over the square root of 2, plus now the sine component, I over the square root of 2. And canceling these square roots of 2's, we then get plus or minus the quantity -1 plus I. So now addressing case 2. This one I opted not to solve with the quadratic formula, and I instead opted to solve this with the difference of squares yet again. So we have r squared minus 2i equals 0. By the difference of squares, we can rewrite this as the quantity r minus root 2i times the quantity r plus root 2i. So let's consider case, I'll call it 2.1 here. So for case 2.1, r is then, well, the square root of 2i. And we can separate this to the square root of 2 times the square root of I. And that is e to the pi I over 4. So let's perform an Euler substitution here. And we will have the root of 2 times the cosine of pi over 4 plus I times the sine of pi over 4. And this time we are talking about this angle right here. So it's going to have the same magnitude of oh, that was off the screen. We'll be talking about this angle right here. And so again, the sine and the cosine components will be the same in magnitude as before, but this time the cosine component will be positive. So back down here, we can then write this as the square root of 2 times the quantity 1 over the square root of 2 plus I over the square root of 2, putting that I term in with it, and this then becomes 1 plus I. So for case 2.2, R must then be equal to negative square root of 2I, and this of course is just the negative of what we had last time. So this is then negative quantity 1 plus I. So we can then write for case 2, R is plus or minus the quantity 1 plus I, combining this and this. So you're probably looking for alpha and beta at this point, not finding them, because typically alpha comes before the plus or minus. And here we have a real and imaginary component, not multiplied, but separated by addition and, well, in both of them. So we don't really have alpha and beta made obvious to us, but let's first take inventory. If we consider all of the terms that we have for R, we have an I plus 1, and we have a 1 minus I, so those are right here. And we also have a negative 1 plus I and a negative 1 minus I. If we consider just these two, now this is, of course, the 1 plus I comes from case 2, and the 1 minus I comes from the negative case right here from case 1. So we're using a solution from case 2 as well as a solution from case 1. But if we consider what these can be written as, this is then 1 plus or minus I. And here the alpha and the beta terms become apparent. Alpha is 1 and beta is also 1. And similarly, if we take yet another solution from case 2 and another solution from case 1, we can then write that R is also equal to negative 1 plus or minus I. And again, the alpha and the beta terms become apparent. So by the same method that we used in the previous example, now that you know how to obtain alpha and beta, both alpha 1, alpha 2, beta 1, beta 2, by the same method as the previous example, you should know how to solve this example. Sorry to do this to you again, but there is one more special case to address, and that's repeated roots. And let's just power through the math. I know that the proof is a little bit difficult to make it through, but once we arrive at the general solution, just like imaginary cases, it's really not that bad. So, whenever b squared minus 4ac yields 0, the quadratic equation will yield the same answers for R1 and R2, because everything after the plus or minus becomes 0. Hence, y1 will be given as e to the negative b over 2a times x. And, well, we can't use e to the negative b over 2a times x as a second value for y2, or a second function, that is, because scalar multiples of a function, as we said previously, don't constitute a basis. So, rather than a scalar multiple, let's consider if there's perhaps a suitable function that we could multiply our solution by, such that it's different from our previous function, but still holds true. So, if such a function exists, let's call it f of x, some function for x. If we take the derivative of this, and we'll have to do the product rule here, so we'll do the derivative of the first times the second times the first times the plus the first times the derivative of the second. So performing the product rule here, we then have f prime of x times the second, which is e to the negative b over 2a, minus, and you can see here the f of x has not been differentiated, but we have performed the differential on the second one, so we have negative b over 2a f of x times e to the negative b over 2a. And we can factor the exponential out from here and arrive at e to the negative b over 2a x times the quantity f prime minus b over 2a times f of x. Okay, that wasn't so bad, just a product rule. Let's go on to y2 double prime. Unfortunately, this one has more product rules. So, performing the product rule again, let's do it first on the first term. So we'll pull down the coefficient of the x term up here. So performing the differentiation, we then pull that down. That's negative b over 2a, e to the negative b over 2ax. And that's times the non-differentiated other part right here. So f prime of x minus b over 2a f of x. And then, of course, leaving this one alone this time, we have e to the negative b over 2a times x. And performing the derivative on this part rather this time, we're then left with f prime of x, double prime that is, minus b over 2a times f prime now of x. And grouping, you can see each of these are multiplied by this exponential, so we can factor that out again. And we do have some like terms. We have negative b over 2a of these f prime of x's here, and we have negative b over 2a of them over here as well. So we have in total negative 2 b over 2a f prime of x. We also have 1 f double prime of x. And over here we have, so we're going to have to multiply these through then. We have negative b times negative b, so b squared, over 2 times a, so 4a squared of the f of x terms. So if a solution for this y2 exists in the proposed form, it's going to have to satisfy this still. So let's move on and see if there's anything that can fit. If we substitute y2 prime, and y2 double prime into this expression right here that we know must be true. It's hairy, but here it is. So we have a times y double prime, and if you remember that looked like this, plus b times y prime. That one was a little bit simpler. Here it is right here. And plus then c times y. Y was the simplest one. No product rules performed. And that must be equal to 0. As we've been doing a lot, let's go ahead and factor out the exponential since everything shares 1. And then aside from the exponential, we're left with what's in brackets right here. So accounting, we have how many f double primes? We have a of them right here, and none of these terms have an f double prime, so just a. And then for the f primes, here we have negative b over a of them times a, so the a's will cancel and we're left with negative b. And there should be one more right here. We have b of them, so negative b plus b, so this term is going to collapse to 0, you can see already. And for the f of x terms, we have 1, 2, 3 of them, right? So we have a times b squared over 4a squared. So we'll cancel this a with one of the ones in the denominator, and we're left with b squared over 4a. And in this term, we have b times negative 2b over 4a, so negative 2b squared over 4a of them. And in the final term down here, we have c of them. So f of x, we have b squared over 4a minus 2b squared over 4a plus c of them. So let's clean this up a little bit. We still have a f double prime of x's, and as we noted here, negative b plus b is 0, so the f prime of x term is completely nullified. And if we combine terms here, we'll see that we have positive c, and then these are actually the same term except we have negative 2 of them here and positive 1 of them here. So combining these, we have negative b squared over 4a of the f of x terms. So we're almost done. Recall from before, as always, that the exponential cannot be 0 because these are all real numbers, and no matter what x is, e will still not be 0. For repeated roots are a special case. If you'll recall from the first page, I think I have that around somewhere. Yep, here it is. We said that repeated roots occur when b squared minus 4ac equals 0. So, if b squared minus 4ac is 0, well, we have a b squared minus 4ac right here. So the coefficient in front of this f of x term is, when dealing with repeated roots, in fact 0. So what this tells us then is that this term right here must be equal to 0 for this to be true. This cannot be 0, and this is 0, so then this must too be 0, so that this entire term becomes 0. So AF double prime of x is 0. We know this. And we also know that A is not 0. Therefore, F double prime of x itself must be 0. So, the function that we're looking for is any function whose second derivative is 0. So let's just state that f double prime of x equals 0, and let's undo a derivative. F prime of x, well, that could be any function with a constant, and only a constant. So let's undo the other derivative and see what f of x could be. Well, that could be, per se, a linear equation. So regardless of what n or m are here, as long as they're elements of real numbers, and this takes a linear form, this will have, in fact, a 0 second derivative. So let's substitute this function into our general form, and then we will, in fact, have two solutions that work for repeated roots and also are linearly independent now. So from before, we had y of x equals c1y1 plus c2y2. And y1 we said was going to be e to the negative b over 2a times x. y2 now we said was f of x, right? So f of x is now some nx plus m times e to the negative b over 2ax. Let's start combining our coefficients as best that we can, and if we combine only the coefficients not multiplied by a variable, we'll have c1 here, and then we'll also have a c2 times m. So c1 plus c2 times m, e to the negative b over 2ax, plus now all the ones that are being multiplied by the variable, so that'll be c2nx, so right there, e to the negative b over 2ax. And since these are all constants, and aside from the x, these are both constants, we can simply re-express this as the general form y of x equals c3, or some unknown coefficient, e to the negative b over 2ax, plus c4 times x, e to the negative b over 2ax. So when your professor or instructor told you that you may multiply a function by x such that it's now linearly independent and still holds, remember, this is very important, remember, and I wasn't told this in my differential equations class, this only holds when b squared minus 4ac is in fact 0. Otherwise, this term right here does not collapse, and f of x cannot be simply a linear function. So, always remember that when multiplying by x, you're only allowed to do that for repeated roots. So now that we have our general form, let's go ahead and do an example. Okay, so for a repeated root example, let's consider the case in which y double prime plus 2y prime plus y equals 0. And like from part 1, I'll go ahead and bring back the initial conditions. So we'll say then that y of 0 is 5 and y prime of 0 is negative 3. So re-expressing this, we have e to the rx times the quantity r squared plus 2r plus 1 is equal to 0. And you can use the quadratic, or you might be able to see the factoring without doing it. It's e to the rx times the quantity r plus 1, quantity squared. So if you FOIL this out, you'll see that this is in fact the same as this. So we can say then that r1 and r2 will be the same, and they will each be negative 1. Reminding ourselves of our general form for the solution, we have that y of x is c1 e to the rx plus c2x e to the rx. And this can be rewritten, if you prefer, as c1 plus c2x quantity times e to the rx. So let's go ahead and impose the first initial condition. It says that y of 0 is then c1 e to the 0 plus c2 times 0. So since this term is being multiplied by 0, we can just go ahead and call it 0. So we're left with c1 times 1, or c1, and we have set this equal to 5. So already we have arrived at a solution for c1. So now we'll need to use the second initial condition to find what C2 must be. So then y prime of 0 will be, let's see, so taking the derivative of this first part first and leaving the second part alone, this will go to 0 and we'll have simply C2 here. So C2 times e to the Rx plus, this time leaving the first function alone and differentiating the second, we will have the quantity C1 plus C2x times R e to the Rx. And if we replace all of our x's with zeros, this will become C2 e to the 0 plus C1 we know is 5, so let's go ahead and put that in there, plus C2 times 0, and R we know is -1 in both cases, so there's a -1 right here, times e to the 0. So this can then be rewritten as C2 plus 5 times -1, and this we know is equal to -3. Moving this 5 over to the other side now as a positive, we will then have C2 equals 3 plus -3, that is, plus 5, so 2. And now that we know C1 and C2, we can replace those in our general form, and we can write the function y of x as C1, which is 5, e to the Rx, plus C2, which is 2, times x, e to the Rx. And of course, at this stage of the video, if I were you, I would want a summary. So, here it is. In part 1 and at the beginning of part 2 here, I did promise you an application, something that this would be useful for. So I spent a little time thinking about something and combined a couple of things in my class notes with a little bit of problem solving that I myself might do. So, if we consider a cart, and we let this cart have a flywheel, and we give it wheels so that it can move back and forth. And let's go ahead and then just mount this with a spring to some kind of a fixed surface. The net force acting on this cart, by classical mechanics, we describe as ma, where a is the second derivative of the displacement. The net force, however, can also be described by the sum of all forces acting on it. So let's go ahead and take inventory of what forces we might see exerted on this cart. There could be some external force, so perhaps you come and push the cart, or perhaps you give it a motor that enables it to spin this flywheel. There could also be damping forces, or things that eat up the energy and cause it to lose its motion. There is, of course, also a spring force, seeing as it's mounted on a spring, so any time it moves in the direction of the spring, being a restoring force, the spring will exert a force on the cart in order to restore it to its equilibrium position. So we can also describe then the net force as the sum of the external force, the damping force, as well as the spring force. Since we have two equations for the net force, let's go ahead and equate them. So we can say then that the net force mx double prime is equal to the external force plus the damping force plus the spring force. Let's move everything without a x over to the right-hand side and everything with an x over to the left. And we'll see that this actually ends up in a form that by now you're probably quite familiar with.
So let's suppose on top the posts of this flywheel cart of yours, up here near the flywheel, you want to mount a motor. And perhaps the motor's external force is given by this expression here, where F0 is the maximum magnitude of the force that it can impart on the cart, and omega represents the frequency. So, knowing this general form for the oscillation of the cart, would it be possible then to put the information that we know into a simulator and fully describe the motion of the system? Well, omega and F0, those are controlled by the flywheel mass and the motor power, so you would probably look at a spec sheet. You would find how quickly the motor can rotate, and you would compare that to the mass of the flywheel and length of the rod supporting the mass. M is simply the mass of the cart. That you could find rather easily by weighing the cart. And K, that's the coefficient for the spring force. And by stretching and measuring the spring and comparing it to the force that it exerts, you could quite easily find that as well. How about the damping force? Well, that depends pretty heavily on the specific system that you're talking about. The friction on the wheels, for instance, if you superextend or supercompress a spring, even sometimes something like air resistance could be a large enough factor. You could run a few tests, but you're hesitant to run the motor without a good guess for what the damping coefficient might be. After all, you could turn it up too high and you could blow your cart away. So rather, you decide to allow the cart to oscillate until the dampening forces return it to rest. And you place an accelerometer on top of your cart in order to measure its position and velocity and acceleration at any point in time. By not including the motor, you've eliminated the external force. This now becomes the homogeneous equation that we're used to seeing. So, let's try to find a way to find this damping force so that we can get a better idea of where we want to set our motor to get the kind of motion that we would expect. So, if you draw the cart back against the spring 2 meters, we can say that at time equals 0, the cart's position is -2. And then if you let it start oscillating from rest, you can say that the velocity, the derivative of the displacement, at time 0 is 0. So, let's assume, as always, that the solutions for x of t take the form e to the rt. And the quadratic form that we'll arrive at will be mr squared minus cr minus k. So, solving for r, we're going to get 2 solutions. I've chosen to denote the positive case as a and the negative case as b. Let's go ahead and substitute these in to the form that we have from before, and we can then say that x of t is given by some unknown coefficient times e to the at. Okay, right? So a is this solution here, and I've left it as a. Now remember, we don't know what a is because we don't yet know c. And then, of course, we'll have to add our second unknown coefficient times e to the bt, and b is the negative case. So if we take the derivative, because we know that we're going to need that later, we'll see that we have simply the same thing, except the first term will be multiplied now by a, and the second term now by b. So let's impose the initial conditions and see if we can find an approximate number for the coefficient for the damping force. So if we consider the first initial condition, where the displacement at time 0 is given by -2, we can say then that c1 e to the 0 plus c2 e to the 0, or simply c1 plus c2 is -2. And rearranging, we find that c2 is given by the negative quantity c1 plus 2. Now for our second initial condition, we know that the velocity is 0 at rest. So at time t equals 0, for the derivative of the displacement, we have then c1 a e to the 0 plus c2 b e to the 0. And let's go ahead and for c2, we'll go ahead and substitute in what we have in terms of c1, and we'll get this down to just one unknown coefficient. And we, remember, still don't know a and still don't know b. So substituting, we then have c1 times a minus the quantity c1 plus 2, quantity times b equals 0. And we can simplify this a little bit, move some things around, and make the expression c1 times the quantity a minus b equals 2b. Let's back substitute a little bit. We know what a and b are, so let's go ahead and put them back in. c1 times the quantity a minus b. So, a minus b, what would that look like? Well, we'll have a c term minus a c term. So the c terms will disappear, and we'll have this radical over 2m minus the negative radical over 2m. So we'll have 2 of these radicals over 2m. So I'll go ahead and cancel the 2, since we have 2 of them, with the 2 on bottom, and it's just the radical over m. So here that is. And over here, we have 2 times b, so I've just put b in here. And of course, we can get rid of this 2 and this 2. So C1 then, if we arrange some things around, can be given by C over that radical expression that we had, minus 1. And you can do this by eliminating the m's from both sides in the denominator, eliminating these 2's, and then dividing each side by this radical expression right here. And you'll see that after you divide that to the other side, you're left with c divided by the radical minus the radical divided by the radical, which is simply 1. Now, c2, we have an expression for that in terms of c1 up here. And since we already know c1, let's go ahead and put that in and see what c2 gives us. So c2 is the negative of c1, so that'll be negative c over the radical, as you see here. And then it'll be minus 2 minus negative 1. So minus 2 plus 1 gives negative 1. So c2 is then given by negative c over the radical expression minus 1. Substituting c1 and c2 into our expression from before, we can now see that we have a function for x of t in terms of c. So we can then say that it's c over the radical minus 1, and that quantity times e to the at. And remember, from up here, a is given by this, and we know everything except for c right here and here. And similarly, the second term becomes, well, simply the negative of c over the radical minus 1, quantity times e to the bt, and like before, for b, we know everything except for c. So everything in this form we now know except for c. So if you were to put this into Excel, per se, and allow c to reference a cell that you can change, right? So it's now a floating variable. And you were to compare this function to the data that you took from your accelerometer, it would not be difficult at this point to try various solutions for c until it matched your data. And when it in fact did match your data, that would then in turn be the c that would represent the damping coefficient for your system. So if you're still with me at this point, I'm guessing you probably liked what you saw. So go ahead and let me know. And if you really like math, maybe you like electronics and electrical engineering too. Go ahead and let Dayton know. He's got some good videos out there. You should check out his microwave gun. It's fun stuff. And if there's other stuff you want to see, leave a comment in the description. We'll see if I can get around to it. It's been great, everyone. I'll see you again later.